Welcome everyone. This is discussion 15, and this will be like our final discussion for today. No, it's been an unusual semester, so thank you for sticking around, and it's been wonderful teaching to all of you. If you have any questions about uh, the class today or class overall, happy to take them. Oh, thanks. Yeah, thanks. I just defended last week. Thanks, Kim. Okay, so the way we are going to do this discussion was so I wanted to first start off with doing the course evaluations. Last time when we did the course evaluations, that was an unofficial way of doing it through Google Forms, but now we have a university mandated way of doing it as you have it for the other courses. So what I'm going to do is I have some instructions for you. The only thing that I forgot to change was the course number, but let me go ahead and share the screen. 1 second. Okay. All right. So we're going to get started with our course evaluations. I'll give you around 10 minutes to go through it. There's one small change here. So you would have received an email from cevals@usc.edu. I'm asking you to fill out the course evaluation specifically for the discussion section. And this discussion section happens to be for BISC-305. This number here, this number here, 13306, should in your case be 13307. Okay. So if you go out and search your email for cevals@usc.edu, you should find an email asking you to fill out the course evaluations. I'm also supposed to read this aloud. So I'll read this out aloud. I'll give you around 10 minutes to finish the reviews. And in the meantime, I'll just switch off my video and audio so that you have complete privacy to fill out these forms. Okay. So learning experience evaluations are your opportunity to provide feedback to your instructor. USC and its faculty take these evaluations very seriously, as they provide valuable information that faculty and schools can use to improve teaching. It is important to remember that the learning process is collaborative and requires significant effort from the instructor, individual students, and the class as a whole. Please provide a thoughtful assessment of your experience as well as of your own effort with comments focused on specific aspects of instruction or the course. Comments on personal characteristics of the instructor are not appropriate and will not be considered. Evaluations should be completed individually with no undue influence by either a student or instructor. Should any inappropriate behavior occur, it should be reported to the Office of Institutional Research. Okay, so in order to be fair, I'm going to switch off my video and audio, and you will have access to the email by cevals@usc.edu. You would probably have gotten multiple emails. And the course that I'm kind of asking you for do this is the particular discussion section for this Wednesday, which is 13307. It says 13306. That's the Monday one, but it's 13307 in this case. All right, so we'll resume in 10 minutes. So 1:14 my time. All right, I guess so. Received around 40% response, which is okay, which is not great, but it's okay. If you have not done so so far, you'll have around 5th of May to go ahead and turn in your, I mean, not turn in, but give the feedback. So if you have not done it so far, you still have around a week to do so. Okay, so the agenda for today was we don't have a handout for what we're going to do today. Instead, what I wanted to do was kind of try to look back. So start from what we learned the latest and try to go back in the process, try to connect the dots, because of what happens a lot in the beginning of the course is you're reading a concept or you're learning about a new concept without actually realizing why you're learning it. But once you start looking it back, it makes it easier to make sense why you were doing it. It also is kind of a good exercise to really understand the concepts in a much greater detail. So what I'm going to do is I'm going to change my screen. Okay. All right. So I'm going to work on a brief review. Before I get started, any questions about anything, any particular, sorry about this, any questions about any particular concept that you would like me to discuss before I get started? Anything in particular? I hope all of you have already turned in your projects. Last time I checked, I think everybody had turned in, so that's really good. And looks like we were on time this time, so it was good to see a smaller density of emails at the last minute. Okay, any particular concepts that is not clear that you would like me to discuss? The exam is on May 12th, so you'll again have 24 hours to go through it. What I've done is I have created a short review handout, which essentially is nothing great, but it's just a collection of all the handouts you have had so far. And it's there on, if you go to the discussions, there's a end term review notes. That handout has basically all the review material that you would need for the end term. It doesn't have the multiple hypothesis testing thing, but I hope that's clear to everyone. Okay. All right. So in that case, if there are no questions, I'll get started. I'm going to switch off my video. So in order to really gauge what this course was meant to provide us, this course in some sense is, if you think about it, starting from what we did in the ends, right? So we start off, we if we look back, the last concept that kind of you touched upon was regression. And regression was essentially a study of how similar are two variables. Right? So in a sense, you were interested in finding out if y can be predicted in some sense from x. And the way we did this was we started off with a very simple model, and this is a linear model. Okay, and it's linear because it's linear in its parameter, right? This is a linear term. There's just one term, and hence it's called a linear model. If I want to look into the relation as to what this linear model is really enabling, so one relation that kind of is interesting to know is this model here is enabling you to kind of capture your variance in y. Okay, why do you have variance in y? Well, because these points are at different heights, and hence you have uh, a variance arising in y. Now, this model, in some sense, enables you to capture this variance. Okay, and the way it enables so is for each value on the x-axis for which you had the y, it predicts a particular value. Okay, and in this process of predicting, it's going to create certain error, what we call the residual. So initially you had these black points, And now for each of this corresponding x value, so this x value is the same between these points. For each of these x values, you now have a new point, which is the predicted value of y. The variance in y, or the proportion of variance explained by the linear model, if you think about it, is essentially variance of dots divided by variance of the black dots. So in some sense, a good model is essentially a better capturer of, so it's able to capture the numerator is essentially equal to the denominator. Otherwise, it's always going to be small. Okay, and why is it going to be small? Well, because at each point you're going to create a residual error. Okay, and in order to fit this line, we essentially relied on this assumption that the sum of EI square is minimized. Okay, and if you essentially minimize the summation, then what you're saying is that this model of linear model, it becomes a unique model. Okay, so this is a unique fit. Now, just to be precise, this is actually y predicted, because at each value, if this is the observed value, then there's a typo there, but I hope everybody understands. So this is observed, and this is beta naught plus beta 1 x plus epsilon I. Okay, and this epsilon is your residual, right? Okay, so that first model was essentially as simple as that. We also learned about how to quantify how similar, so quantifying similarity. How do you quantify similarity? We do this in the form of correlation coefficient, which is R. Okay, so you'll have access to all the formulas. So my task today is not to revise these formulas to you, because you know already what these formulas are. You have access to them in some sense, and this will remain throughout your life, right? So you'll always have access to the formulas. What you should be able to retain out of this course is the conceptual understanding, right? So why are we doing things the way we are doing it, and why should we think the way we are being asked to think, right? So correlation coefficient R is in some sense quantifies, and it's a great number because it's a number between 1 and -1, indicating how similar are or how dissimilar two quantities are. And this proportion variance that you see here is essentially, in case of linear models, is essentially a square of this correlation coefficient. Okay, and this relation always holds. So this relation always, so not here, but this relation always holds if your model is linear. Okay, so and for this class, our all our model, the most complex model that we'll be learning is a linear model. So in essence, this is essentially in some sense the entire history and the entire summary of your regression. Okay, so the task that we had at hand was to be able to find out the relation between y and x. We chose a model, and this model that we chose is the simplest possible model because it's a linear model. This linear model essentially captures the essence of how y relates. This is your intercept beta naught and the beta 1 slope. So beta 1 is essentially quantifies. So we are again, all the times, all the terms that you see here are quantifying some relationship. So it quantifies how much y changes for a unit change in x. Okay, so if x changes by 1 unit, then y changes by beta 1 units. Okay, and beta naught is quantifying how much y you have when x is 0. Okay, as simple as that. Okay, so that was essentially our understanding of the relation between two continuous variables or discrete variables in some sense. Now, if we go back and we look at what we have been doing so far in the class, is actually we so far have been interested in differences between two groups. So whenever you talked about hypothesis testing, whenever you talked about um, t-tests, whenever we talked about any non-parametric test, we so far had been doing hypothesis test. Okay, and hypothesis test are, and I'm going to classify them in the same domain. Our interest was given two groups or multiple groups. So first was we started off with a plain hypothesis testing. And we said that you're given these two groups and you're interested in identifying if they have either the similar mean, or in case of non-parametric version, do they arise from the same distribution, or G1 and G2 are from the same distribution. Okay, and we were interested in identifying whether this really holds or not. And in order to quantify that, we needed certain assumptions. Okay, so in some sense, if your case A was that the data is not paired, and if we required that, so we, in order to be able to do any sort of test, we required them to be simple random samples, and we required independence. Okay, we did not explicitly identify, or we did not explicitly identify whether the particular groups were independent or not, but however we learned about what really independence means. Okay, what does independent mean? So independence essentially means that the probability of an event A happening given that B has happened is not dependent on B. Okay, and this essentially implies A, B are independent. Okay, so when you were learning just about this in probability, it didn't make sense. But if you think about it now, it's kind of is an important fact, because you can now verify whether a certain event is independent or not, for which you require this particular concept from probability. I'll just take a brief detour and quickly review what are some important concepts that came from probability. The first concept was about quantifying what is the probability that if A and B are two events, what's the probability that A happens or B happens? Okay, and a common misconception often is this is just this. Okay, however, that's not right, because I'll show you next how. It's this. And why is it this? Because we start off with an event A. We also start off with an event B. Now, this is like a very general case scenario of any two events A or B, right? This intersection here could be 0, it could be anything. So this case here essentially encompasses all sorts of possibility. It is also quite possible that A and B happen to be subsets. So B can be here also. So what I'm drawing here is just representative. The exact intersection value, which is this, does not matter how much it is. Okay, it could be totally encompassing B, or it could be totally 0. And how did we reach till this point? So in order to reach that point, we started off thinking in a different direction. We started saying that in order to be able to calculate A or B, the first area that I need is this. And this area is PA minus PA and B. Why? Because, well, this area here is PA and B. There are no doubts about it. Both A happens and B happens in this small area. Similarly, this area here is PB minus PA and B. So if you sum 1, let me write that in the same color. So if we sum 1, 2, and 3, you will get this value here. Okay, so this value is equal to 1 plus 2 plus 3. This relation always holds. So star always holds irrespective of what A and B are. One more related concept that we learned about was how do you condition, right? So how do I find what's A and B, which is represented as A and B? That's very simple. I can again condition it on B. So probability that A and B happens is equal to probability that A happens given that B has happened multiplied by the times the probability that B happens. This is also equal to PP given A, PA. This is again a star, which means it always holds irrespective of what A and B are. Okay. So these are kind of the two important ideas that you need to keep in mind, and that's basically everything that you would need for solving any problem in probability. Okay, given a particular condition of let's say A and B independent, then this becomes equal to PA times PB, and this is, let's say, a delta, or let's say a circle indicating that only if A, B are independent. Okay. So when you were learning about probability, this was the motivation to be able to understand what really independence is. Okay, and for which we essentially went up through a lot of exercises trying to quantify what is the probability of A and B and what's the probability of A given B. One related concept there was of probability trees, where you looked at two events happening. So let's say you're a smoker or not, and not you, but somebody else. So if somebody is a smoker or not, and what's the probability of developing a disease, which is C, NC, C, NC. Okay. So probability trees are essentially one way to represent these conditional probabilities. Okay. So for example, this branch here essentially represents probability of getting disease C, given that the person was smoker. Okay. And similarly, this one here is probability that you develop a disease C, given that the person was non-smoker. One more thing that we learned was to kind of law of total probability, which was this. So probability that I have a disease C, what is it equal to? So the only other event I have is whether that person was smoker or non-smoker. Okay. So either I could be a smoker or I could be a non-smoker. That's the only two possibilities. And now you know this. So you have basically been able to divide this into two events. But now using this star formula here, you can quantify what it means to have an AND probability there. Right? And this is just one way to break it down. Depending on what you have in hand, you can break it the other way down as well. So this is PC plus P. Okay, these two are equivalent forms. Nothing is right, nothing is wrong. They are basically both equal, depending on what you have. So if you are working with, if you have PC in hand, then that's something that you're going to work with. Okay, if you don't have this PC, then you're going to work with, if you have PS in hand, then this is the quantity that you're going to work with. Okay. And that essentially sums up your probability trees and probability entirety. We'll go back to talking about paired and versus non-paired sample. So when we started assuming that these two conditions are satisfied, and we then went on to, sorry, this keeps popping up. The next question that we asked is the data normal? Okay, so are the two groups normal? And if they're normal, your choice of test is the parametric version of test, which is called a t-test. And if it's not normal, then we learned about the non-parametric version of tests, which are called, in this case, Wilcoxon Man-Whitney. Okay, so you asked two questions. The first question that you asked, is the data paired? No, the data is not paired. The next question that you asked is the data normal? Then if it's normal, then you're going to work with these two groups and do a t-test. If it's not normal, then you're going to do a Wilcoxon Man-Whitney test to be able to test the differences. We also saw a different scenario where the data was paired. Okay. And think about what really happens when you make data pairs. So G1 and G2, these two essentially are coming from the same patient. Okay. And similarly, these two readings are coming from the same patients or the same person or the same entity, whatever it is. And in this case, now your assumption of independence no longer holds, right? So these two, this is no longer independent. This is no longer independent because there is a coupling involved here. Okay. However, they're still, in some sense, SRS. This is true. But the next question that you ask in order to be able to test is it normal? If it's normal, you're going to do a paired t-test. Okay. And the only thing that differs between doing a paired t-test versus a normal unpaired t-test is how you calculate the standard deviation. Because the standard deviation here is in some sense coupled to each individual, and hence it has a different variation of the formula as compared to t-test. Okay. So the important thing that you have to figure out working with any two group sample, is it paired or is it not paired? Okay, that's the first question that you should ask. The next question you ask, is it normal or is it not? Okay, and depending on that choice, your choice of test changes. We also saw how do you check for normality. If you want to check for normality, the easiest way to do is do a QQ plot. Okay, and everything should look like a linear line here on a QQ plot. If it's not normal, we saw multiple versions of these tests. We saw a sign test, which just looks at signs. We looked at a sign rank test, which is essentially also called the Wilcoxon sign rank test. Okay, so it's again a non-parametric way of looking at things. It looks at the ranks, it looks at their signs, and then decides whether there is enough difference between two samples or not. Okay, fair enough. So we, I now hope that you'll be able to make sense of why we cared about independence and why we cared about probability, because one thing that's really important for doing these tests is to verify whether these conditions are met or not. Okay, and these conditions require you to really be able to understand what does it mean for something to be linear, what does it mean for something to be independent. Okay. Okay, then we go to ANOVA. And in ANOVA, we kind of generalized our assumption. Okay, so now you have three or maybe more groups. The question that I'm asking is still very similar. Is the mean of these three groups different or not? And in order to do that, we have this choice now. So equipped with our knowledge about doing a t-test between, let's say, the assumption of normality is satisfied. So all these groups or all these columns are individually normal. Then one choice we had was to do a t-test. But t-test will lead us to an inflated number of false positives. So just to be clear, this is pairwise t-test, not simply just t-test, because t-test is designed for two groups only. I'll also quickly give you an overview of what does it mean to be a false positive. And hence, so this option, it's not option one, but it's an option that's ruled out. So we designed ANOVA for multi-group analysis, right? And this ANOVA, if you go by the name, is analysis of variance. Hence, it's able to basically, in some sense, capture the variance between the different observations. Okay, so just to review, what does it mean to capture that? So imagine you have these groups G1, G2, G3, and the reason I'm drawing this color in blue, the rows are indicated by the green color. The question that you ask is you calculate what's called a F statistic, which is essentially a ratio of your between variance. So B always comes before W, so B is in the numerator, okay, if you have trouble recalling it. Again, this is also one way which you can kind of remember this throughout your life. So this is between versus within. Okay, now what's between? So it makes sense to have it in the denominator, in the numerator, right? Because what you're essentially looking at is how different are these two groups, or how different are these two groups. So we look at this blue quantity, which is essentially variance of your columns. Okay, it's not variance, it's essentially sum of your squares, but that's equivalent for all practical senses. The next thing that you're looking at is I'm looking at how much amount of variation can be explained if I look at only the columns after having accounted for the variance that exists in the rows. Okay. And these rows, when you're looking at these rows, you've completely forgotten about what these columns are anymore, right? These rows are essentially all the data that you have. And if this quantity is large, so if Fs is high, that means you will generally reject your H0. Okay, and you can see why, because there seems to be a lot of variance between, or a lot of summation, lot of difference between the columns after having adjusted for the fact that the data itself has a lot of variance. Okay, and this value statistic is high, leading you to reject H0. Okay, and that essentially summarizes your ANOVA. I have a few more minutes, so let me just quickly give you a review about what is a false positive. So false positive, which is essentially how we based our hypothesis testing. Okay. So in order to think about p-value, one thing that you would always keep in mind is when you define H naught is true. Okay, this is your basis for defining false positives, for defining false positives, for defining p-value. This is the true underlying fact. Okay, so H naught is true. You are already basing your assumption that H naught holds. And the next question that you're asking is, well, if H naught is true, let's say, sorry, I'm not able to draw this. Okay. So if this is your t distribution, and this is again on the fact that H naught is true. Okay. Before you do any experiment, before you do any hypothesis test, you base your observation on the critical region. This critical region, if I'm doing, so this is alpha by 2, and this is alpha by 2. So I'll just make it explicit. HA is non-directional. Okay. So before you start on any experiment, you say that if I observe a t statistic which is going to be greater than either of these two, so if it's higher than t alpha by 2, t less than minus t alpha by 2, then you will reject H naught. Okay. Why? Because the probability of observing something as extreme as this is very low. Okay. Because this height here at each point indicates the probability of observing that particular statistic in some sense. It's actually the probability density, but for all practical reasons, you can assume that to be probability. So if you observe a t statistic in this region, then you will reject your H naught, saying that, I started off with this assumption that the H naught is true, but it does not really hold because I'm observing a quantity which is the probability of observing something as extreme is very small. Okay. However, let's say that H naught is actually true. Okay. So you know that the null should hold, and you get a t statistic which belongs here. Okay, so this is t statistic which is observed. What will I do? At this point, I'll say
It's the probability of observing something. I just needed a critical alpha of T alpha here, and this is more in the extremity. So I'm going to reject H naught. And this is going to create a error, okay, which is called a type 1 error or a false positive. Why is a false positive? Well, it's because H naught is true, but you're rejecting it. Okay. And that's what essentially forms your false positive. Okay. Is that clear? Okay. So I think that was it from my side. If any of this was not clear, feel free to ask me. So we still have few minutes. So one particular question that one particular part that I kind of skipped was this idea of association tests. Okay, so association tests are simple chi-square test, and in that sense, what you're looking for is, let's say, you have two categorical variables. So categorical one has two levels, let's say f and m, whatever they are, and categorical level two has, let's say, uh, let's call it G and N. Okay, sorry, this is messy. So this is categorical. Okay, so you observe 10 quantities here, you 5, you observe 1 here, and 5 here. Okay, and the question that you were asking was, is there any association between categorical 1 and categorical 2? Okay, the moment you see this, the moment you see two categorical variables which are kind of organized in this kind of format, just think about a chi-square test. Okay, so I'll not write down the formula for that, but this should just give you a way to think about any problem. Okay, so what over the past few years, when I've been a TA for this course, what I've noticed is sometimes students just fail to realize what the problem is really asking. So just spend some time to think about what is it that you are releasing, right? So if it's arranged in this kind of format, ask yourself a question: what variables am I looking at? For example, like doing an ANOVA in this case is not going to help, right? Because I'm asking a different question. I'm asking for an association question. If the question had been that if I was looking at one particular continuous variable which had these two categories, then you could have done something like a two-way ANOVA to ask how one particular category influences that continuous variable. But the question here is completely different. The question here is essentially arranged in terms of counts, and these counts are arranged in terms of tables between the two categories, right? So if you do an ANOVA in this case, first of all, I don't know how you'll do it, but even if you end up doing it in some sense, then that will be wrong. Okay? So think about what problem is asking you. Think about what domain of the problem does it really belong to. Okay, and I've kind of tried to lay down all the domains that you would uh, end up focusing, end up coming across in either the exam or even in most of this actually applies very generally, right? So even when I do testing or hypothesis testing for my research, I ask this exact same question that I showed you. Okay, so I don't remember all the formulas obviously because you'll have access to all the formulas. It's important, however, to be able to understand what is more applicable here. You can always figure out what formulas apply, and now you have access to R, so you can just do any testing. And in your process of realizing and doing this in R, you would have realized that R does not tell you if you're going to do an error. So if you do an ANOVA on discrete data, it won't throw an error. But ask yourself, are the assumptions really true or not? Okay. So just relying blindly on the software is not a good idea because the software does not know what assumptions need to be satisfied. Okay. In most cases, it will not show an error. Okay. So I think that was it from my side. If you have any questions, please let me know. I'll also have my office hours again next week. Uh,
but you're welcome to email me asking me about anything. Oh, what's considered an high FS? Okay, that's a great question. So you'll have to consult the table for a high FS. Let me go back here. But something like 30 plus is going to be generally okay. So what's high FS? 30 or more. Okay. This is like a conservative way of saying it. It depends obviously on the degrees of freedom of your numerator and denominator. Okay. But if you have 30 plus, in most cases, you're going to reject your F naught, H naught. Okay. All right. Okay. All right. Great. Thank you. Thank you, everyone, for sticking around. I know it's been a particularly different and difficult semester, uh, but it's amazing to see all of you join me every week on this discussion. And I hope if we don't meet, I don't think we'll be able to meet, but if we don't meet, I'll wish you good luck for your future. I'll stick around for a couple of minutes, but you're free to go. And if you have any questions, obviously, let me know. All right. Thank you, everyone.